Okay, so where we're at, we have this figure of an object moving around a circle of radius r, angular velocity omega, mass m, theta is the angular position, and of course we could figure out the arc from that. And v is the velocity of this object, and v without the arrow over it is the speed. Okay, the kinetic energy of the object is 1/2 mv squared. Its velocity is r omega. That's the magnitude of its vector velocity. So its kinetic energy is 1/2 mv squared, which is v being r omega, which is then 1/2 mr squared omega squared. And that's what we call 1/2 I omega squared, where I is mr squared. So I being mr squared, let's think about these two objects. And let's say that the 3 kilogram object at 0.8 meters and the 2 kilogram object at 1.2 meters, 1.3 meters, are connected by some massless rod so that they're one system. So what we have is the 2 kilograms moving around the 1.3 meter circle and the 3 kilograms around the 0.8 meter circle, both at 5 radians per second. Obviously, the 2 kilogram object will be moving faster than the 3 kilogram object. The total kinetic energy, and I don't know how I got up there to smudge that, but I must have, is 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared. And of course, we could calculate the speeds, multiply the number of radians per second by the radius, and just use v, so it would be 1/2 mv1 squared, m1 v1 squared, 1/2 m2 v2 squared. But we're going to do it like this, okay? And plugging the numbers in, as it turns out, and I'll go over this calculation a little more extensively in another video, in a subsequent video, if we do these calculations, I1 being 1.92 kilogram meters squared, I2 being 3.38 kilogram meters squared, the I1 being calculated by this simple calculation using I equals mr squared, we get 66 joules, which was the total that we got for the first and the second object. I think it was 24 joules here and 42 joules here. Okay, we'll go into a little more detail in the next video. Okay, I let myself get a little bit in a hurry on that last video, but I left us with the idea that we're going to explain some of these calculations, and I apologize for getting in a hurry. I was trying to squeeze that one in to avoid getting over the maximum length, and it looks like I went over by 2.29 seconds. So should have talked a little faster, said a little less, but that wouldn't have necessarily been a good thing. Okay, so again, we have the 3 kilogram, 2 kilogram masses moving with common angular velocity 5 radians per second because they're attached now by a strong but a rod strong enough to support them but of negligible mass. And we want to calculate the moment of inertia of the entire system. Now we already know that without using moment of inertia, we were able to determine that this one had a kinetic energy of 24 joules, this one a kinetic energy of 42 joules, just using a 1/2 mv squared and directly calculating v. But we want to calculate these now using the moments of inertia. One change from last time, I had an omega 1 here and an omega 2 here. Since the two are moving at the same angular velocity, we don't need to have subscripts. We can just call the angular velocity omega, the common angular velocity, being 5 radians per second. Now, I've gone ahead and substituted all the necessary terms. The moment of inertia I1 is 3 kilograms times 0.8 meters squared, using the fact that moment of inertia of a mass at distance r from the axis of rotation is mr squared. And I've done the same here with the 2 kilograms and the 1.3 meters. So I've got this expression just represented here. In the next expression, or in the next line, I made a little bit of a jump. I multiplied this out to get 1.92 kilogram meters squared. I multiplied this out to get 3.38 kilogram meters squared, which we've already seen. I don't think we've actually calculated the 1.92 kilogram meters squared. But implicitly, I've factored these out. Well, what I've done is I've factored out the 1/2. Here it is. I've factored out the 5 radian per second quantity squared. Here it is. And what I've got left here is just this and this. That should be fairly easy to follow. So now I've factored it out and I've got my 2 moments of inertia. Well, I might as well just add them. So I kind of got this in parentheses. It's not really part of the expression. Maybe I shouldn't even use an equal sign. I'll put this in parentheses and just say that that's what this is, and the equality continues here. Okay. So I add these two, I get 5.30 kilogram meters squared. Multiply that by 25 radians per second quantity squared, and do the arithmetic. And lo and behold, it comes out 66 units are kilogram meters squared times radians squared over seconds squared. And that will equal 66 joules, but let's deal with this whole idea of radians squared and meters squared, okay? The meters squared, radians squared, and the units here. The meters squared, well, those are meters of radius, because remember where the meters came from, okay? It's, you know, one of them came from the radius of this circle, another from the radius of this circle when they were combined here, okay? So those are meters of radius, and the radians, of course, are angles in radians. If we multiply a meter of radius by an angle in radians, we get a meter of arc. So a meter squared of radius times a radian squared of angle gives us a meter squared of arc. And the meter squared of arc is where this thing's moving. Now, you can have some small arguments with that, but that supports the idea that if you multiply meters by radians, you get meters. And if you divide meters by radians, as long as you're dividing meters of arc by radians, you get meters of radius, which kind of justifies the way radians are used in these calculations. Now, you don't have to keep track all the way through a complex problem of whether a meter came from a meter of arc or a meter of radius. You just kind of accept that if you multiply a meter by a radian, you get a meter. If you divide a meter by a radian, you get a meter, and you hope you got it right, and generally you do. If you've done your reasoning correctly, it works out. I advocate rigorous use of units, but that's a little more rigorous than what you usually see in a course. We just kind of wave our hands and make the radians go away and appear wherever they need to. Okay, anyhow, we do end up with kilogram meter squared over second squared, which is joules. Now, another important idea then that we get from this example. Remember, we added the moments of inertia and did this calculation. We got the same thing that we got when we did the individual kinetic energies, not even using moments of inertia, okay? But our conclusion here is that the moments of inertia of individual masses can be added to give us the moment of inertia of an entire object. And in this case, the entire object consists of these two masses on this light rod. And the kinetic energy of that object is, if they're just two masses, the kinetic energy is 1/2 I1 plus I2 times omega squared. So we can speak of the I1 plus I2 as being the I total, and we see that moments of inertia can be added. So if we have an object consisting of many masses, we can extend this argument, and we can add those moments of inertia to give us the moment of inertia of the complete object. And if that object is rotating then with some known angular velocity, we can calculate its kinetic energy by just doing 1/2 total moment of inertia times omega squared. So we can speak of an extended object, as long as it's a rigid object that's rotating about some axis, we can speak of that object as having a single moment of inertia, which is, which is the sum of the moments of inertia of the individual masses that comprise it.